So the next chapter is about acids and bases, and we're going to think about those in terms of equilibrium. But first we have to get through some definitions. So the most common definition for acids and bases is the Arrhenius concept, where an acid is a substance that produces H plus or hydrogen ions, okay, when it's dissolved in water. So if I take an acid where I have a hydrogen ion and the anion that pairs with it so that it's neutral, okay, so A here just means a generic anion, then that's going to dissociate in water and create a hydrogen ion or a proton. Often we'll call that a proton, and the anion that pairs with it. A base is a substance that produces hydroxide ions when dissolved in water. So here's a generic definition. You've got, usually it's an ionic bond, so you have a metal with hydroxide. So that's an ion pair. So when they dissociate, you get the metal positive ion and the hydroxide anion. So one example is HCl. If I put HCl into water, then it's going to dissociate into hydrogen and chloride and increase the hydrogen ion concentration. An Arrhenius base is something like an ionic solid, like NaOH, that when you dissolve it into water, it separates into sodium ions and hydroxide ions. Arrhenius acid-base reactions, then, if you add an acid to a base, then the hydrogen ion that was dissociated from the acid combines with the hydroxide ion dissociated from the base to make a molecule of H2O. So you can often think of H2O being made up of as a hydroxide plus a hydrogen, right? So that makes a water molecule. The cation from the base combines with the anion from the acid, that's the leftover stuff, to make a salt that's typically an aqueous salt. So we have HCl plus NaOH. You can see that the hydrogen and the hydroxide are going to get together and make water, liquid water. And the whatever's left over, the chloride and the sodium, are going to get together to make sodium chloride. So in general, in the Arrhenius picture, we have an acid plus a base makes salt plus water. So this is a useful picture in many ways, but there are probably as many different definitions of acids and bases as there are contexts. So this particular definition does not explain why molecular substances such as ammonia dissolve in water, because that's not an ionic bond. They do not also contain hydroxide ions, so that doesn't really make any sense for it to act as a base. And it does not explain how some ionic bonds, such as sodium carbonate or sodium oxide, dissolve in water to form basic solutions as well. It does not explain why molecular substances like CO2 or carbon dioxide dissolve in water to form acidic solutions, even though they don't contain any hydrogen ions. And it does not explain acid-base reactions that take place outside of an aqueous solution. So the definition that we are going to be using the most in general chemistry, and probably you'll use it a lot in organic as well, is the Bronsted-Lowry definition. In the Bronsted-Lowry definition, an acid is a substance that can transfer hydrogen ions, which means they can donate in a reaction a hydrogen ion. So we call it a proton donor. Okay, again, if you have a hydrogen ion, then the one proton nucleus has lost its one electron, so it's just a proton. Okay, so that's why we call it a proton donor. Bronsted-Lowry base then is a substance that can accept that hydrogen ion, so we call that a proton acceptor. Okay, so whenever we think of Bronsted-Lowry acids and bases, we think of them in the reaction context. We usually don't think of them alone, like you do in the Arrhenius context, where you could just put HCl in solution, it'll dissociate, or you just put NaOH in solution, it'll dissociate. Bronsted-Lowry acids and bases are always defined with respect to each other, right? So they need to be reacting with each other in order to be defined. So again, here's a generic acid with your proton plus the anion that's going to counterbalance the charge. And then you've got a base, okay, and the base is going to be that hydrogen ion acceptor. So when the base accepts the hydrogen ion, it becomes an acid, and this is a conjugate of this. And you'll notice that the base and the BH plus, right, these two species are exactly the same, except for this one has an extra proton. The acid HA, right, and the conjugate of that, A minus, this is the exact same molecule, except that it has lost a hydrogen, okay? So we call these pairs of species conjugate pairs. And when I identify a conjugate pair, I'm identifying the two species that look exactly the same except for the hydrogen ion that has attached to it. So the acid and the base are not the pair, right? The products here are not the pair. It's the B and the BH plus that is a pair, and the HA and the A minus that are a pair. Within the pair, we call them an acid-base pair because this base is a base. It can accept a proton. And this species is an acid because it can donate this proton, okay, away. So we have an acid, we have a base and an acid pair. Those molecules look exactly the same except for an extra proton or extra hydrogen. Okay, so conjugate acid-base pairs are chemical species whose formula differ only by one hydrogen ion. When we think about acids, then, if we want just to identify HA as an acid, then you can write it as a reaction with water. Okay, so here we have HA acid reacting with water. So I'm going to put that into water, into solution, react it with water, and this acid is going to dissociate and give up its proton, and that proton is going to be accepted by water. So in this case, water is the base, and that's going to produce hydronium. So hydronium is H3O plus, okay? And this is the actual form. Like if you just have an acid dissociate in water and separate into a proton and the anion, the proton does not just hang out in solution by itself. It will always associate itself with another molecule. So whether that's a base, right, to make a conjugate acid out of a base, or water to make hydronium, okay, this proton will not just be floating around in water by itself. So a more accurate picture here is for hydronium to exist, not H+. But you'll often see those two things written as synonymous, and I'll try to point those out as we move along. Then what's left over from this acid HA is this A minus species, right? The anion gets left by itself. And so HA and A are an acid-base conjugate pair, and water and hydronium are an acid-base conjugate pair. How we write this is no longer HA goes to H plus and A minus. We always write this as a reaction with water, right? What is it going to do when I put it into water? This is going to dissociate, but the hydrogen ion is going to now associate with the base. Base association is similar. No longer are we going to write this as a metal with a hydroxide, because those are ionic species and they will just dissolve into metal and hydroxide. But if you have a covalently bonded compound, right, molecular species like ammonia, this also acts as a base, because when you put that into water, okay, this base can accept a proton. So my hydrogen here on my water is going to be stolen by ammonia, okay, to make hydroxide gets left over from water, and my ammonia accepts that extra proton to become ammonium ion. So the ammonia and ammonium are an acid-base conjugate pair. They're the same molecule except for that extra proton, and water now turns into hydroxide. So putting this base, ammonia, into water does increase the concentration of hydroxide, just like in the Arrhenius definition. But it doesn't do it by dissolving because it doesn't have a hydroxide in it. It doesn't dissociate and release hydroxide. Instead, it steals this hydrogen ion, steals the hydrogen ion from the water to leave hydroxide over. So we can first practice identifying what conjugate pairs are, right? So what is the conjugate base of this acid, pH4+? And what is the conjugate base of this acid, HCO3-? Well, again, a conjugate pair is going to be the exact same molecule except for a difference in a number of hydrogens. Okay, so if this is an acid, this pH4+ is an acid, it's going to give up a hydrogen so that the conjugate base is just pH3. Okay, so it's not just giving up a hydrogen, it's giving up a proton, which is an H+. So you get rid of a H and you get rid of a plus. Okay, so you end up with pH3. So that's how we identify what is the conjugate base of this acid. The acid will donate a proton, it'll get rid of it to somewhere, and what you'll be left over with is the same molecule except less one hydrogen plus. So we can do the same thing here with HCO3-. What is the conjugate base of this acid? Okay, I will remove, this will donate its proton H+, and what I will be left over with is the same molecule less the hydrogen plus. So I'll get CO3-2-. That's the carbonate anion. We can do the same thing with the conjugate acids of these two species. So here's our cyanate anion. This is a base, and it is going to accept an H+. So if I do Cn- plus an H+, I'm going to get HCN, and my charges are going to cancel out. So I get HCN is the acid conjugate of this base. Same thing here with HCO3-. I can add, this will accept a proton H+. Okay, the minus here and the plus from the proton are going to cancel out, and I'm going to get H2CO3. So this is the conjugate acid of this base.